Yeah, g'day, it's Charlie ZL2CTM. Well, today's video is going to be an interesting one for me, in that it's going to be a bit of some playing around, a bit of some experimenting. So what I'm looking at the moment is the bandpass filter. And before I look at look at those, this is what it essentially is. It's a doubly terminated Butterworth maximally flat response circuit. It's based on some filters out of the back of the solid state design for the radio amateur. These are filters that I've used before. And as we can see here, a couple of tank circuits that are linked through this coupling capacitor here, called notionally C12, with a couple of additional capacitors on the end, which are used to match the filter to 50 ohms that this is designed to connect to. When you look at the tables at the back of the solid state design for the radio amateur, you're given some values here, and then you essentially calculate what the capacitor needs to be in parallel with the inductor to bring that particular parallel tank circuit there to resonance. So in this particular case, for 80 meters, you're given C0 224 picofarads, C12 here 8.8 picofarads, and Cn to 83.4. As you'll see down here, I've just taken the nearest standard value, so 83 picofarads, I'm going to use 82. For the coupling capacitor there, rather than 8.8, I'm going to use 8.2. And as you'll see later on, I'm actually going to use, for experimenting, some trim capacitors that run between 5 and 40 picofarads. Now the inductors here, I've elected to use 38 turns of number 24 on a T68-2, so the -2 is the red core for 80 meters, good for sort of 3 to 10 megahertz. And like I say, I've taken the nearest standard values for C end and for the coupling capacitor, and then what you need to do now, based on whatever you've chosen and whatever you're using, you then work out what the parallel capacitors need to be to bring things to resonance. So in this particular case, you take C0, or 224 picofarads, minus our end capacitors, which are going to be 82 picofarads, minus the C12 is 8.2, comes out 133.8. And as you'll see, what I'm going to use 120 picofarads in parallel with this trim capacitor, like I say, that runs between 5 and 40 picofarads. The 40 meter one, exactly the same configuration, obviously some slightly different values, and as you'll see over the back, once we get to it, for the inductors, I've got two different types I was playing around with. I've got a T68-6, which is the yellow core, and a T50-6, so a slightly smaller one there, also yellow core. I'll put this up on the blog, so I won't go through the calculations there, but as we can see here, the Cn was 53, I'm going to use 56. Our coupling capacitor between the two circuits, or the two tank circuits, was 7.2 picofarads, I'm going to use 8. And then working out what the parallel capacitors need to be, 178 picofarads. And I'm going to use 150 in parallel with that same trimmer. So that's what we have over the back here. So these have actually been liberated out of one of the radios, or a couple of the radios and bits and pieces I've been playing around with over a while, which I'm no longer using. This particular one here, as you can see, was, I'm trying to get the reflection of the light, was a combined circuit onto the one earth plane there, and we'll have a look at that in a sec, with just the switches to switch between the 40 meters and 80 meters. And then the second one over here, they were separate ones, which I've just mounted temporarily on an earth plane there to do some tests. And as you can see there, for the 40 meter ones, the slightly smaller T50-6 versus the T68-6, so slightly different. Anyway, so what I wanted to do for a start was to compare the insertion loss between this configuration here and this configuration, and then I wanted to see if I could reduce that insertion loss as much as possible. And I understand it's more than likely in these particular circuits here that a lot of your losses come from the type of capacitors you have. And as you'll see, what I want to do is play around with trying some polystyrene capacitors here. and I've got a whole lot more out in the garage with different values. So I'm going to look to use these in lieu of the ceramic capacitors. I'll keep the trimmers for now, and we'll just see if we can't make things a little bit better. So I'm going to stop and start this video several times, and over the next few days just have a bit of a play and see what works out. So for today's experiment I'm going to use the Nano VNA. Not a lot of people like this. I find it quite useful, and what I'll try and do is just have everything in the same picture. So if I was to short input to output, you can see the straight line across the top of the screen at 0 dB. So anything below that line in terms of dBs would be an insertion loss. So let's start playing with say the 80 meter ones. So we'll go separate for a start, and excuse me for doing this on camera, but I'm not going to do right. So I'm currently sweeping between one, as you can see down the bottom of the screen there. Let me just go like that. Sweeping between 1 and 30 megs. I'll change that. We'll make a start of say 3 megs, and we'll make a stop of say 4.5 megs. And we can now start to see the way in which the coupling works between those two parallel circuits. So this is the one here. If I was to now slightly adjust that coupling capacitor between the two, that's C12, you can see how that has an effect. We start to reduce down now, we start to get a little bit more loosely coupled, our bandwidth increases, our 3 dB points, but then we start to get quite a noticeable drop in the middle. So it's a bit of fiddling around there, trying to, what I've found is trying to maximize the flatness to get the kind of bandwidth that I'm after. In this particular case, the values that I've selected should give a maximally flat response between 3.5 and 3.7 megahertz. At the moment the cursor is sitting on 3.510, and we can move that through to the other side, which is now 3.78, so quite a bit larger there. But what I wanted to point out for recording is, if we were just to have a bit of a tinker around here, and for argument's sake just say select that as a bandwidth, we can see there that at that cursor we have an insertion loss of 1.07 dB. So not too bad, and pretty well in line with expectations out of the design notes. So what I'll do now, I'm just going to very quickly shift to the other 80 meter. So that 80 meter one there was this one here, so that was one that was separate. And we'll now just shift across to the one that's on the combined circuit board. A bit hard to try and see there, so that goes to there. If I was a teacher, I'd say talk amongst yourselves for a few minutes. Click there. Right, so there we have, make sure we're on 80 meters, which we are. That's now, as you can see, the second filter, and if we were to play around with its coupling capacity, we'll see exactly the same sort of effect. So let me just start to see that there. Now if we were to bring that around to roughly the kind of bandwidth we're after. Let's just move it around. I'm not going to use the touch screen. So that's 510 on this side here, across to 5.7. So pretty well maximally flat there, as you can see, across for in this particular case, but an insertion loss of minus 5.2. So a good sort of 4 odd dB greater than the other one for effectively the same components, which is interesting. Yeah, so that raises questions. Is it because of this arrangement here, where I've tried to have two filters in parallel? Arguably they're electrically separated by the switch, but is there any other kind of effect going on? or is it this arrangement here that with some long surfaces here that we're getting some additional capacitance between these, effectively a plate here and earth? Is that causing some issues? I don't know. So what I want to do, I want to have a bit of a play around with that, and I don't know if I want to play around with this one or play around with the other one, but I'll probably play around with this one as a starting point. And like I say, I'm going to, over the next few days, replace these ceramic capacitors with the polystyrene ones and just see what the effect is. So that was for the 80 meters. If I was to change bands, so I might as well keep it in this configuration here and change to the 40 meter band, and we'll change our sweep frequency from say 6.5 megs to a stop of, let's go with say 7.5, which is 200k greater than our upper limit here of 7.3. Oops, that should have been 7.5 megahertz, and we can see that there. Now it looks fat there if I was to go right back out to say 1 meg through to, in fact you start to see it there, to say 10 megs. You can see the pass band there, and straight away you can see that, and I'll zoom up in a sec, we're talking about minus 7.53 dB. Let's go back to another start of, like I say, 6.5 megs, and stop. This is just me just talking as I'm playing around here, so apologies for that. To 7.5 megs. So this is that filter here, and again if I was to tinker around, and I've done this before playing around, and I could not get it anywhere near the same sort of losses as, or insertion loss, like the 80 meter, which is interesting. Yeah, so there you go. So let's just arguably say that we're talking around that sort of minus 7 dB of insertion loss, which is way too high and certainly outside the expectations of a doubly tuned filter. So something's going on there, and I don't particularly want to throw that in the circuit and have that much loss on the signal. If I now swap to the other 40 meter filter, so go to there, we'll go to there, earth goes to there, and we go to there, and we can now start to see the other one there coming up. Let me just move that to get the reflection out of the way. Right, so same sort of story. I don't really need to play around with this one. I've sort of maximised as much as I can. You can see the right hand here is 6.6. For us, it would be, that's, the bandwidth is way too high there. So if I was to try and tighten that up a little bit, so reduce the coupling between the two, just to tighten it up a bit. But by doing that, I also sacrifice some insertion loss. So again, just tweaking. I'm now just you might be able to see in the back of the camera there, just tweaking those two parallel capacitors in parallel with the inductors, just changing the overall resonant frequency of those tank circuits. That's probably, in terms of trying to minimise the, or not minimise, but to yeah, make the bandwidth about right. So 6.8 is a bit too low, coming through to 7.2, 7.3 is about the end, and as we can see here it's sort of minus 7.66, which is pretty similar to the other filter, which had the smaller T50 -6 cores. Anyway, again, way too high from what I'd like in terms of insertion loss. So I need to go and have a bit of a play, and a bit of a think, and a bit of a fiddle and experiment to see if I can't make that any better, or at least try and get the 40 meter performance to be something similar to the 80 meter performance, because minus 1.5 to 2 dB, that's fine, that's great. That's good. So if I can get the 40 meter one to be similar to that, then life is good. So I'll just pause there. So apologies for sort of rambling and the way this is put together, but that's just sort of me just sort of documenting what I'm playing with. And like I say, if something new comes up, the aim is over the next couple of days is to sort of record things and I'll stitch together at the end and see where we come about. Okay, we'll see you soon. Okay, so I have replaced the two ceramic capacitors that were in parallel with the two inductors, with two polystyrene capacitors you can see there. At this stage I've left at the input and the output the two ceramic capacitors that are acting as the impedance matching. I might, yeah, well at this stage I'm going to leave it at the moment like it is, for the simple reason, if I was just to zoom back out again, that has made a huge difference. So I think that's going to be in focus with no reflection on the light. As we can see there, the cursor is currently sitting on 7 megs, so that's the bottom of the 40 meter band with minus 1.8, and if I was moved down to the far end, so 7.3 megs, minus 2.4. So that's a considerable difference between what we had before and now, and certainly in line with my expectations for this particular filter. So that's really good. Now if we were just to zoom out, so start, let's go say to 1 meg with a stop of top end, and we can really see how effective it is there, right up the top there. So that's good. So that was a huge difference there. So I'm sort of quite tempted to do the same thing with the 80 meter band, even though the 80 meter band from an insertion loss point of view wasn't too bad. It would be just quite interesting to see how I get on with that. So in the end I used two 150 picofarad polystyrene capacitors, which is what I was not quite exactly what I wanted. Ideally I needed 100 and I was going to use, sorry, no, the calculations came out to be 178 and I've used 150 in parallel with that 5 to 40 picofarad capacitor, so I'm certainly in Kiwia where I need to be. So that's really good. Alright, I'll just pause there and I think I might have a quick fiddle with the 80 meter one and see how we get on there. Okay, same story with the 80 meter bandpass filter. I've now replaced those two parallel capacitors with 100 picofarads. So 100 picofarads in parallel with that 5 to 40 to give me 140 total, where I'm after roughly 133 was the design calculation. So certainly in the ballpark. And if I was to come back down to the plot, we can see there, let me just see if that's in focus. I think it is. We can see there that now, because the 80 meter band is a huge band from for here in New Zealand, 3.5 through to 3.9 megs, the design bandwidth for the filters is between, well, they're basically 200k wide. So in this particular case I've chosen 3.5 to 3.7. So if I was now to go down to the lower end, which is there, we can see that's 3.5, so we're just inside the 3 dB point, and reasonably flat all the way across to 3.7. 3.7 is minus 1.48, minus 1.7, peaking up to 0.93, back down to 1.5, so not maximally flat, but my goodness, yeah, pretty good as far as I'm concerned. For an insertion loss of roughly max 1.5 dB between those two frequencies. So a slight improvement on what I had before. So I think, conclusion wise I would have to say it really is, which I've read before, a factor of the where's that shadow coming from, sorry, a factor of the type of capacitors you use. Yeah, I don't really have anything else at this stage other than the polystyrene and the I guess the cheaper ceramics, so I might have to do a bit of looking around, but I do have a whole stack of those out in the garage, so I guess I've got enough to last for a while. Anyway, so that was an interesting exercise. If anything else crops up over the next couple of days, I'll throw up another video. I think because I don't have the exact values for the two, just to go back to here, the two end capacitors that provide the impedance matching to 50 ohms, I'm reluctant to use another value because I lose that impedance matching, and in all honesty I'm quite happy with, pick a number, minus 1.5 dB insertion loss, so trying to scrape another half dB is not particularly really worth it. So I think I might just leave those values in to try and give me the best match to 50 ohms. Anyway, so yes, interesting exercise. Like I say, if anything else crops up, I will join onto this. Otherwise, I'll join it together and I'll throw it on up. But yeah, quite interesting and something to bear in mind, and I'll add that to my book of notes for the future. Okay, cheers all.